35. What were you about to say? Every single one of them? I don't have them written down, so I don't know what they are. These were all particle motion, right? I don't think so. I mean, it's in the particle motion section. I'm not going to lie, I just saw the word problems of the ones we hadn't done yet, and that's what I gave you. But it's in the particle motion section, so I assumed. Okay, although the November 1959 eruption on the island of Hawaii began with a line of fountains along the wall of the crater, activity was later confined to a single vent in the crater's floor, which at one point shot lava 1,900 feet, wow, straight into the air. Oh, do what was on the board. Just do what was on the board, not what was on there. I'm sorry, it's probably because it's last year's class, and I thought that it was, I probably just forgot to change the numbers. At least you didn't do it yet. I did half of them. I was wondering why it was so high. Did you have 35? That was on the board. I will make a conscious effort to make sure that the homework that I write on here, that I update it on campus. Okay, so let's see. Initial velocity. Good morning. You missed our inspirational dot day read through earlier. I know. We heard Reginald the raccoon read the dot, and then we created an inspirational post-it for the math department. Okay, back to particle motion. If initial velocity is the exit velocity of a particle of lava, its height t seconds later will be, well, there's your position function. What's v sub 0 mean? Initial. Anytime you see a sub-zero, that's initial, so that's initial velocity. Begin by finding the time at which, what are they asking? Oh, what was the lava's exit velocity in feet per second and in miles per hour? So it says begin by finding when the SDT is equal to 0. Neglect air resistance. So let's see. It looks to me like, so which at one point shot lava 1,900 feet in the air. All right, tell me what you think we do. Anybody? What are we going to do about initial velocity, though? Well, 1,900 feet, that's the... It wouldn't be 0. If initial, look at the hint. If initial velocity is the exit velocity, if initial velocity of is the exit velocity of a particle of lava, its height t seconds later will be. I think we're going to need the initial velocity here. Did any of you work through this one? Let's put a pin in this one. Let's go to another one. Give me a different one. 7, like number 7. Let me hook the camera up so we can see this graph. So here we have fruit flies. Gross. Sorry, y'all. I'm going to have to dig a little deeper in that volcano problem. All right, let's take a look at this graph. What is the derivative of this going to look like? So if this is the function, part A asks us to graph the derivative of the fruit fly population. What units on the horizontal and vertical? So looking at this is my, think of it like a position function or a regular function. So if I do the derivative, this is it. What are the units here? Days and flies. So if I do derivatives, if I do the derivative, that's slope, right? So what would the rate be? Flies per day, right? Does that make sense? Flies per day. Okay, so if I do flies per day, what is the derivative here? Because that was the first part of the question, right? What unit should be used? So what's on horizontal and what's on vertical? Horizontal is days. You want to keep them the same? So what's it going to look like? All right, so this is my first. Henry says an upside down parabola. Looks like the slope is close to 0, right? Is it increasing or decreasing? Increasing, and it's coming and it's getting pretty steep, but it's always increasing, right? Do we see that? Always. So something like positive, always increasing, so it's always positive, but less positive. Something like that. Is that what y'all got? And they could be, it could be a little less, so you mean it was more like that. So as I'm looking at this graph, right, I'm thinking, remember I'm talking about slope as I do this. So let me think about what the tangent line would look like. So the slope of that tangent line. And if you notice, it gets big, but then whenever it hits somewhere in the middle right here, it's still positive. It's still a positive slope, but it starts getting closer and closer to 0 again. So it starts out close to 0, it gets bigger, bigger, about right here, which is going to be about right here. It stops getting as big, but it's still a positive slope. So it starts getting closer to 0. Does that make sense? A little bit. During what days does the population seem, and we kind of just answered that, but looking at this, you can actually use this graph instead of your derivative graph. During what days does the population seem to be increasing the fastest? Why in the middle? Why there? It's the steepest. The slope, that's exactly right. The slope is the steepest, somewhere around probably 25 days, because that's where the slope is the biggest. If the slope is the biggest, it's changing the fastest, right? My rate of change is the biggest. Rate would be how much? Does that make sense? You okay? When does it seem to be increasing the slowest? That's right. I would say at the very beginning, right? Because that's when my slope is almost 0. And then at the very end of 50 days, because that's when it's evening out this way as well, and slope's getting closer and closer to 0. That make sense? And you said number 8. Didn't somebody say number 8? 8's a good one. Bless you. Did anybody work through number 8? The number of gallons of water in a tank T minutes after the tank has started to drain is given by this equation. How fast, and whenever I talk about how fast, I'm thinking speed, I'm thinking what? What goes along with speed? Velocity, right? Velocity is the rate, that's going to be the rate here. So that's kind of what I'm thinking. That's why it's in here with particle motion stuff. So how fast is the water running out at the end of 10 minutes? And then what's the average rate at which the water flows out during the first 10 minutes? So I'm looking at two different things. Can you determine what the two different things are that I'm looking for? You're exactly right. IROC and AROC. IROC is coming from how fast is the water running out at 10 minutes, and then AROC is the average rate at which the water flows out during the first 10 minutes. Do you see the difference there in what they're asking? All right, so let's look at IROC first. What do I do? Derivative, exactly. Did y'all find the derivative this way, or did you multiply it out? Y'all are gonna have to multiply it out because we hadn't learned chain rule yet. So, go ahead. So that works, but what we're fixing to learn is you also have to take the derivative of what's inside. So just since we haven't done chain rule yet, let me just multiply it out. So I got 200 times 30 times 30 is 900 minus 60t plus t squared. So that'd be now can we find the derivative? What's the derivative? Negative 12,000 plus, that's right. So IROC is easy here, right? Because I just plug in that value for, what is it, 10 minutes. So what is the derivative at 10? What is it? Negative 8,000 what? Gallons per minute. Does it make sense why it's negative? Why? It's losing water. That's right. It's draining out. It literally says the number of gallons of water in a tank after the tank has started to drain. So it's losing 8,000 gallons every minute. Does that make sense? As the water drains out, it's draining out 8,000. Okay. Then it says, what's the average rate of change over the first 10 minutes? So what shall I do? Ten and 0. You're exactly right. So I'll do when time is 0 minutes, and then I'll do when time is 10 minutes, and all I'll do is find the slope between them. All right, so 0, I'm back to that original equation, remember, because it's just slope. 30 minus 0 squared, which is that right? Did I do that right? Oh, yes, because this should be big, right? What is it that I'm finding at t equals 0? The amount of water in the tank whenever I first start. So that makes sense that it's big. Gallons. How about 10 minutes? I should have a lot less, right? Because if I'm losing 8,000 gallons every minute, then Q of 10 should be a lot less than Q of 0. 20 squared, 200 times 400. No, where did I mess up? I got too many zeros on. No. Oh, I don't have enough here. There we go. So 180,000 gallons to start with, and now I'm down to 80,000 gallons. I still haven't done what it asked me to do because what did it ask me to do? That's right. I have to subtract them. 80,000 minus, what am I dividing by? Yeah. So this is slope, right? So it's change in y divided by change in x, or change in t. So it's what I found here divided by the change in time. So I don't know what you get there. Somebody tell me. I hope it's 10,000 altogether. Is it? Negative. Yes, because if I started with 80,000, this would be negative. Yes or no? See the difference there? See how my average rate of change is different than my instantaneous rate of change? They're not so far off that it's unbelievable, but they are different. All right, what else? Gracious, another draining tank one. You said 25? It takes 12 hours to drain a storage tank by opening the valve at the bottom. These are typical AP questions too. Draining a tank because you can go into the negative velocities, the draining the, it's just. All right, here we go. 1 minus t over 12 squared meter. So this is, the depth is y, t is hours after the valve is open, and there's my formula. Find the rate at which the water level is changing, and they even tell you that is nothing more than dy dt. So to find dy dt, I need to expand y just a bit so that I can find the derivative, right? So I'm going to do 1 minus t over 12. This will be a lot easier when we learn scaling. T over 12, that would be 6 times. 2 of those would be t over 6 plus t squared over 144. Is this what you all got for? You sure? Everybody get that for y? Didn't know how to do which part, the foiling of it or the derivative of it, or you just looked at it and said, I don't think I'll be able to do that, so from the, okay. You want me to show you out to the side what it, okay. So I did 1 minus t over 12 minus t over 12 plus t squared over 144, right? These two together, since they have the same denominator, negative t minus t would be negative 2t, and then 2 divided by 12 would be 6. It's a little confusing with the fractions. Now that it's in the form of a polynomial, it's a lot easier to take the derivative, right? Say right, because it is. Thank you. All right, so what's dy dt? Negative 1 plus 1 over 12. Why is it 1 over 12? There you go. 1 over 24 t squared. So if you multiply by 2, 2 over 24 t, which is 112. So that's part A, right? And then it says, when is the fluid level in the tank falling the fastest and the slowest, and what are the values of dy dt at this time, or at these times? Tell me what I need to do. Think in terms of particle motion and how I find a biggest value and a smallest value. If I'm talking about the fastest and the slowest, then I'm talking about what? The velocity or the derivative, right? So how do I find max and mins using the max and mins of the velocity like that? How do I find when it's fastest and slowest? Say again. Graph it. We can graph it. If this is velocity, right? This is a linear function. Do you agree? Everybody okay there? So if I were to graph this, -1, and then I go up 1 and over what? So this is dy dt. What does that tell me? Any idea? How do you know it's the slowest at 12? Velocity is 0. Remember, speed has to do with the absolute value of velocity, right? So if I'm talking about the speed, how fast it's coming out, just because velocity is negative, and velocity is negative here, right? Just because it's negative doesn't mean it's not coming out fast. Or it doesn't mean it's going back in. Remember, that has to do with my direction. This is when velocity, because what's my interval here that I'm looking over? Does it say? 12 hours. So 12 is as far as I go, so I'm stopping here. That's when it's the slowest. Does that make sense? Are you sure? Would it make sense that that's when that's the slowest? If you're draining something out, right? You've got this big urn of something that you've got a hole in the bottom. Whenever you first start draining it, it's coming out really fast, right? But then it starts slowing down as you get to the bottom of it until it's just a trickle at the end. So that's what they're getting at here. Okay, so when is it the fastest? At the beginning, whenever you first start. This right here would have the biggest absolute value. Does that make sense? And what are the values of the derivative at this time? So what is dy dt when x is 0? -1. -1 what? What are my units? Meters per hour. How about at 12? What's the derivative at 12 and what does that mean? At 12, 0 meters per hour. It's done draining, right? Nothing's coming out anymore. Everybody good? We just graph them. The other would be a parabola. What else? What else? What else? Are y'all ready to step away from particle motion for a minute? Preston said absolutely. Okay. '34 is 34 is a good one. Inflating a balloon. And so let's see. You would not. It's in feet, right? So I've got volume 4/3 pi r cubed. The volume of a spherical balloon changes with the radius. What rate does the volume change with respect to the radius? So I'm looking at dV. If you can write your d statement, it'll help you with the units. So dV, derivative of the volume, with respect to what? The radius? What units is volume in? Because I'm talking about feet here. Cubic feet. Squared would be area, volume would be cubic. So feet cubed per what? Foot. That's exactly right. That's exactly right. Think about what this means. As you blow air into a balloon, the volume is increasing however much for every foot of radius that you give it. So as the radius increases by a foot, it's telling you how much the volume is increasing. That's why it's feet cubed per foot. But if you can write this, it's a lot easier to get the units. Did that answer your question? It said that the radius was in feet. It said, what rate does the volume change with respect to the radius when r equals 2 feet? So if the radius is in feet, the volume has to be in cubic feet. If it was area, if it was the derivative of the area with respect to r, it would be square feet per foot. 26. The graph shows the position S of a truck traveling on a highway. The truck starts at t equals 0 and returns 15 hours later at t equals 15. So we're going to graph the velocity curve. No, what does it say? This is the graph the truck's acceleration. So this is the velocity graphed, and they want us to graph. So essentially the derivative of this is what we're going to graph, right? Let's see. Can't even focus. Can't even answer a stinking question. Well, if I do the derivative, it's going to look, so I'm at 0, I'm starting out, it's not quite a line, but it starts out almost linear, but then it starts getting steeper faster, maybe something like that for the velocity. And then the acceleration will actually look close to that because I'm positive. I'm almost a constant slope, but not really a constant slope. So it's going to be higher up. So maybe it's something like almost constant, and then it starts kind of working up as well. Yeah. Yes. Look, I'm still shook up. It's going to be linear, but it's going to go, you're right. It's going to start out positive. So do something like, and then go negative here. So about what? Actually, it's going to get, as it gets steeper, that means it's going to go something like that. So what you got? And then acceleration, always negative, always. These are so dumb. Negative and then steeper. And steeper, as you go. Let's move on from particle motion. I'm done with it. That's okay. Some of these you will learn very quickly. I'm going to walk you through a couple of them where we will derive it so I can show you why it is what it is and how it is. So should you forget it on the exam and you have extra time, you could actually go back and find it. You will find it way more beneficial just to memorize them, however, but it can be done. We will start with just the basics. And that would be the first. We'll go up through cotan. We'll go up through cosecant today. So on your green sheet, starting with sine, That row, 1, 2, those 3 rows there of trig functions. We won't do the inverses today. They're hard. But we'll stick with the sine, cosine, tangent, and then the cofunctions also. All right, the derivative. I don't know that I need to write all these, but we will. The derivative of sine x, cosine x. But the derivative of cosine x is negative sine x. We will actually, in just a minute, we will do the difference quotient, and I will show you why that works. And then this is probably one I think that you'll do on your homework. Maybe. The derivative of tangent x is secant squared x. What does secant mean? 1 over cosine. That's exactly right. These are the ones that you'll really secant squared x. It's the same thing as 1 over cosine squared x. The derivative of secant x, this one's an easy one for some reason to remember too. These first 4 are probably the easiest. Past that, you really start getting in there. Yeah. Secant x, tangent x. We'll do some more Kahoots or something to try to help you remember these. Come some flashcards or something. Is it better if you write what? Yeah. Yeah, the order doesn't matter. The derivative of I should have went in order on your sheet. Cotangent x is negative cosecant squared x. Gross. And then finally, the derivative of cosecant x. This one's hard for me. Negative cosecant x cotangent. We're going to be doing lots of manipulation with trig functions. We go through here. I don't think I want to walk you through something. Tell me how you feel. Do you want me to walk you through a proof of a couple of them, or would you rather just use them? Using the difference quotient to prove to you why the derivative of sine x is cosine x. Do that? You won't want me to do this on all of them, I promise. But just to show you. The derivative of sine x. So let's think about that difference quotient. Difference quotient says the limit as h goes to 0, f of x plus h minus what? F of x divided by h. And I have to try to manipulate it some way to get it where I can plug in 0 for the h, right? So let's plug in what we know here. We've got sine of x plus h. I've got to do the limit as h goes to 0. Sine of x plus h minus the sine of x over h. What in the world can I do to manipulate this in any way whatsoever? I gave you a sheet a while back. I don't think I have a copy up here. It's laminated. All the important ones are laminated. And it's got your trig identities on it. I hope this one is on there. Do you have an angle sum identity on there? Angle addition? Yes. What is the sign? How can I expand that out? Should be angle sum identity. Say again? Yes, yes. So the limit is h goes to 0. It's time what? Uh-huh. Yep. There you go. The minus sine x is still there. Y'all okay? This is stinky, isn't it? I told you. All right, so now what can I do? What in the world am I going to do? Any ideas? I'm going to manipulate these a little bit so that I can take something out of somewhere. So is there something that you see that at least two of those pieces have that I can take out? Sin x. I'm just going to move it around a little bit. Remember, this is all manipulation all the time, just to try to get it to the point where I can cancel something out or put in something that I know so that I can then simplify down. All right, so sin x, cosine x. I'm going to move this negative sin x here beside it so you can actually see what's happening. And I'm going to leave this cosine x sin h over here to the side. And I'm going to take a sin x out of just those first two terms. Oh, there's an H. I did work this one prior to make sure that this way worked because we could go a million different directions trying to do this. All right, limit h goes to 0. Take a sin x out of the first two. What do I have left? Cosine h minus 1 plus. I still don't really see anything that I can do here. So I think what I'll do is split this up into two different fractions. Are y'all okay there? So I'm going to make this, remember my limit properties. I could make this, the limit is h goes to 0 of sin x plus the limit as h goes to 0 of cosine x sine h over h. Are we okay there? This looks like something I might could work with because they have the same variables. Yes? So maybe I say, okay, another property of limits. The limit as h goes to 0 of sine x times the limit as h goes to 0 of cosine h minus 1 over h. I don't know that you will ever have to do this. This just increases your skills of understanding. That's why I asked y'all first if you want to see it. And I'm going to do the same thing over here. The limit is h goes to 0 of cosine x times the limit as h goes to 0 of sine h over h. So I split it up with multiplication this time. Well, this is just sine x, because there's no h in there anymore, right? And this is just cosine x, because there's no h in that, times the limit as h goes to 0 of sine h over. This is one we've done before. Do you remember what it is? What'd y'all say? 1. Right? Remember, we did the limit as x goes to 0 of sine x over x, and we just said it's 1. So I know that one. So I know this is cosine x times 1. But how about this? That's that limit. Remember whenever we graphed it before? And it did like some funky stuff like that. And we found out that this was 1. The limit as it got closer and closer to 0 was 1. That's one of those we did. How about this one? I think we're going to have to do a graphical approach on that too. Agree? Disagree? No, okay. Greer, you just look like you're just off somewhere else right now. This is hard. This is hard. That's why I was hesitant to even do this first, because I'd already done it one time and I knew what it entailed. If you graph cosine x minus 1 divided by x, what does it look like? Yeah. Well, here, I'll pull up Desmos. Cosine x minus 1 divided by x. That's not going to help. Yeah. That's probably going to help a lot. I was about to say, oh my gosh, what in the world? Okay, so yeah, so what does it look like it's going to as you approach 0? 0. Make sure your minus 1 is not inside with your cosine like mine was. Yeah, mine wasn't either. Parentheses around the top, yes. So parentheses cosine x minus 1, and then close your parentheses and do divided by x. So I get sine x times 0, which is, of course, 0. Cosine x times 1 is cosine x. Therefore, the derivative of sine x is cosine x. That's what I'm thinking. If you look at it whenever you graph it, as I approach 0 from both sides, it goes to 0. I will say, the basic trig functions, oh, no bueno trying to derive them like that. But some of your others, like secant and cosecant, I have on a test before gone through because I could not remember for the life of me, and I've done it. They're a little bit easier and not quite as bad, but you have to be so well versed in those identities to be able to do it. Like if we didn't know that very first identity, and I'm not going to lie, that's not one that I have memorized, then we'd have been screwed from the beginning, right? Nope. Not one like that, no. And honestly, if you can memorize those, you'll have to do this. These kind of things are good for working with trig functions because you'll have some things on the exam where you'll have to be able to manipulate and work with and cancel out, and you'll have to know some trig identities to do that. The amount of that on there is minimal, but it does pop up. And we'll have to do some algebraic manipulation with trig functions, so you'll need to be able to work with them. But something this extensive like that, I've not ever seen. That's pretty rough. Well, I asked y'all first, and you're like, yeah, show us. Okay, let's do some examples the way you're going to have to do them. You'll have to do some deriving of them, but nothing that intense. Let's do look at the right one. In the wrong stinking section. Straight from your home. Number 2 simply says to find dy dx, and I have y equals 2 sine x minus. This green sheet is going to be your best friend. Dy dx. What's the derivative? Excuse me, of 2 sine x. And 2 is the constant, the coefficient in front, so I can bring that on around. It's just going to be in the front of the derivative. And what's the derivative of sine x? Cosine x. I bet you'll never forget that now after all that. Minus, what's the derivative of tan x? That's it. That's all you do. That's not bad. How about number 6? Y equals 3x plus x times tangent x. Find the derivative. You do this one. I just heard my key. Special needs. 3 plus. Did you use product rule? I hope you did, because that's what you have to do. Derivative of the first. What? No, yes. Did y'all see that was, what did y'all do then? What? Oh, no. Okay. Let's do product rule. Derivative of the first, which is 1, times the second, plus the first times, what's the derivative of tangent x? Secant squared x. Well, I know it's terrible, isn't it? I'm going to stop there because Actually, let me see. I had 28 written there. Yes, that's it. 28 says to show that the graphs of y equals tangent x and y equals cotangent x have no horizontal tangents. So you know a little bit more about derivatives and things like that. In order to have a horizontal tangent, what has to happen with the graph? Anybody? Horizontal tangent means max or min, right? Because that's where the slope changes. It goes from positive to negative, negative to positive. Look at the graph of tangent x. Do you see why it has no horizontal tangents? Why? There's no max or min. It's always increasing. It never starts decreasing. Thank you. Does that make sense? And then it said also show cotangent. If you're putting cotangent on your calculator, by the way, you'll have to do 1 over tangent. But it's the same thing. It's always decreasing. There are no max and mins, which means it can't have a horizontal tangent. Okay, I'm going to stop for real this time. You would say because the function is always increasing for tangent and always decreasing for cotangent. It would have no horizontal tangents, or it has no horizontal tangents because it has no maxes and mins. It never changes direction. You're going to do 1 through 10. We already did a couple. Those should be super duper quick. And then 21 through 30, which is still just using those. You'll use those derivatives to write equations of tan lines.